It is well known that water is the key compound, the key ingredient to all life as we know it. Here on Earth, water is plentiful. Makes sense that we have so much life here. Most of the biochemistry that living organisms use takes place in water. Here we're going to be talking about solutions. A solution is when you have a homogeneous mixture of at least two substances, a solvent and a solute. A solvent, simply whatever you have more of. The solute is whatever you have less of. So in the case of most water-based solutions, water is the solvent. There's a special name for those solutions. Aqueous is the term that is used. Aqueous solutions are often electrolytic solutions, and an electrolytic solution is something that contains electrolytes. Those are dissolved ions that would conduct electricity. For example, if you take a spoonful of salt, sodium chloride, and you put it in water, the sodium chloride would fall into individual ions. Those would be the solute, and the solvent would be water. Now, sodium has a positive charge, chloride has a negative charge, so you would be able to send an electric current through that solution. Those ions are considered to be electrolytes. As it turns out, most ionic compounds are actually electrolytes, but not all. We'll talk about why that is a little later. Take a quick note of the bottom bullet point here. A solution is better able to conduct electricity if it has more ions that are present. That's going to be an important point for later. For example, sodium chloride can yield 2 ions per 1 formula unit, but potassium sulfide would yield 3, 2 potassiums and the 1 sulfide. The potassium sulfide would better conduct electricity. Often, when ionic compounds dissolve in a solvent, it's represented as a separate chemical equation. Here we can see sodium chloride in its solid crystalline state disassociating, that's the key word there, disassociating into sodium and chloride ions. Notice the AQ, that stands for aqueous. Anytime you see that, you're dealing with a water solvent. Notice here at the top, ionic compounds will dissolve in polar solvents. Polarity is the idea that you have some sort of solvent as a molecule that has positive and negative aspects to it. Water is a good example of this. In fact, water, as the primary solvent of life, is as such because it has a positive and negative pole that allows it to dissolve all sorts of things. In this image, we can see sodium and chloride are each being surrounded by water molecules. The negative pole of the water is attracted to the sodium, and the positive poles are attracted to the negatively charged chloride anion. Notice that the chloride and the sodium would love to be together, but in this case, they are more attracted to the water than they are to each other. That's the difference. Not all ionic compounds will be attracted to the water. Some will remain more attracted to each other. Notice also that the sodium ion can actually fit more water molecules around it. That's an important note. You see here we've got two different ions. We have a cesium cation and a lithium cation. Both have the same charge of +1, but the lithium is smaller. There is something here called a greater effective nuclear charge experienced by the lithium. If you think about it, any molecules, in this case water molecules from the solvent, any water molecules surrounding it will be able to get closer to the positively charged nucleus of the lithium. That means that more water molecules will actually be attracted to the lithium. So that lithium ion is going to experience more drag as it tries to go from the positive towards the negative pole of this electromagnetic field. The cesium ion, even though it's larger, will travel faster. So key point here, the smaller the ion, the more effective nuclear charge it experiences, and the slower it will move through a field or through a solvent because of drag. Molecular compounds may or may not conduct electricity. Most do not. Acids, which we learn a lot more about later in the course, they do. However, not all acids conduct electricity the same. For example, only a very small percentage of acetic acid, that's the acid in vinegar, dissociates in water. even though it is very soluble in water. Because a weak acid like acetic acid experiences only a little dissociation, only a little bit of electrical current can be conducted. Now, we assume that strong acids completely dissociate in water. However, there's always a small percentage that does not. Because strong acids experience complete dissociation into charged species, they are generally extremely good conductors of electricity. We can see here that electrolytes have three categories: non-electrolytes, weak electrolytes, and strong electrolytes. Again, non-electrolytes would be molecular compounds that don't dissolve at all. Sugar is a good example. Weak electrolytes are things that do not dissociate completely, but do a little bit. They form some ions in solution. Weak acids are an example there. And then strong electrolytes could be the strong acids or ionic compounds that completely fall apart, completely dissociate, such as sodium chloride. This is a good time to become familiar with our strong acids. Here are the big six of strong acids. You really do need to memorize these. The sooner the better. We have perchloric acid, hydroiodic acid, hydrobromic acid, hydrochloric acid, nitric acid, and sulfuric acid. Sometimes regular chloric acid is also considered to be a strong acid. That would make 7. You need to memorize these and know that they all form the strongest of electrolytes in solution. Any other acid that is not on this list, or chloric acid, are considered to be weak acids and do not completely dissociate.